So today we start lecture 13 in helicopter dynamics course, and this lecture is going to be devoted to normal mode equations. I'm Dr. Ranjan Ganguly. So now what we are going to do is we are going to presume the solution of the governing differential equation of a dynamic system can be written in terms of the various normal modes. So here the modes are phi1, phi2, phi3, phi4 and so on. And then remember that corresponding to each of these modes there is a time dependent part. This is the modal coordinate. So we call this xi1, xi2, xi3, xi4 and so on. These are all Greek letters. So essentially this is an approximation that the response can be expressed as a series of normal mode terms. And this becomes an approximation when we truncate this series. If we were to use all the modes here, we would have a complete set for a discrete system, and then we would essentially just normalize the equations. But one of the advantages of the normal mode transformation is that we can use a truncated set. So here we of course know phi1, phi2, all these from the solution of the modal problem. So here I am presuming that you have found the eigenvalues and mode shapes for the problem. You know the natural frequencies and the mode shapes. So therefore what is to be determined are the psi1, psi2s and so on, and once you determine them you can get the solution Wt. So for simplicity and practicality, let us assume a 4 degree of freedom system. So generally all the analysis I am doing is valid for an n degree of freedom system, but let us say we have 4 masses connected by spring. So from our previous lecture you know that the degrees of freedom would be x1, x2, x3 and x4 corresponding to these 4 masses. Now what we are going to do is we are going to presume that you have found the stiffness and mass matrix corresponding to this system, and then you have calculated the natural frequencies and the mode shapes using the method described before in a previous lecture, and therefore you know phi1, phi2, phi3 and phi4. There will be 4 modes here corresponding to 4 natural frequencies corresponding to 4 degree of freedom. So what we are going to do is we are going to express the solution only in terms of the first 2 modes. So we are going to use a truncated series here. So that's the 2-term expansion, and we have decided to represent the response of this 4 DOF system, which has 4 normal modes, by using the only first 2 modes. So essentially in matrix form I can write this equation as a vector phi1 into phi2 into xi1 and xi2, and remember that these two are typically vectors. So now let's go back to the general differential equation for a multi-degree of freedom dynamic system. So it's in this form. Now in this special case, this happens to be a 4x4 system. Now we are presuming a 2-term solution here. So let's take this 2-term solution and plug it back into the differential equation. And if we do that, we get this equation here. Now looking carefully, you can see a lot of the things in terms of the dimensions here. So the mass matrix would be 4x4, as would the stiffness matrix. Force vector would be a 4x1. But here I am considering these two matrices here. So essentially this modal degree of freedom is a 2x1 system because there are only 2, and this phi1 and phi2 are 4x2 systems because each of these has 4 rows because there are 4 degrees of freedom, and of course there are 2 of these columns, so this is a 4x2 system. So all this multiplies out well. If you multiply this and this, you would get a 4x1, and so all of these would be 4x1. So essentially you have a reasonable system of 4 equations here. Now this is the 2-term solution which we have written out, and now what you do is you take this and you pre-multiply this by this vector here. Now you can clearly see why I would be pre-multiplying. Essentially, then I can use the property that phi m phi would normalize this particular mass matrix and also the stiffness matrix. So we're going to take this and pre-multiply this equation here. So I do that in the next slide and I write this whole thing out. And here you clearly see that this into this into this would be there. These are all matrices which we can multiply. So this is 4 by 4, 4 by 2, 2 by 4. So if you multiply this, you get a 4 by 2, and 2 by 4 multiplied by 4 by 2 would be 2 by 2. So it becomes a 2 by 2 system. So now we will draw on our knowledge of the normal mode transformation and realize that this particular phi t m phi would essentially create a diagonal matrix, and also phi t k phi would create a diagonal matrix. So that's our complete equation after the pre-multiplication by the mode shapes, and using the fact that the modes are normal, I can then write this equation out here. So essentially what has happened is this entire thing has become a diagonal matrix. This entire thing has become a diagonal matrix, and your degrees of freedom are now the modal degrees of freedom xi1 and xi2, and so we have written this equation out. Now these S1 and S2 are defined as modal forces, so you can see clearly from here that it would be phi1t into F. So you would have to calculate these modal forces here. So this is a nice looking equation, and you can see what has happened. The 4 degree of freedom system has been expressed as a 2 degree of freedom system now, and also these two equations have been decoupled in the sense that now there is only the xi1 term in the first equation and only the xi2 term in the second equation. So to make it very concrete, let us write this out in actual form. So we remove the matrices here and bring it back into this form here. So I can write m1 into this double dot term plus this term into this term equals s1. So you clearly see that these are two uncoupled equations. The topmost term only has xi1, the bottom equation has xi2. So essentially what I have managed to do is I have managed to write this multi-degree of freedom system as single degree of freedom systems. So that's one of the key simplifications which comes about by the normal mode transformation. And if we were to expand this in our thinking and consider that you would have a coordinate r, so then what would happen is that the mass would be this mr, the stiffness corresponding would be mr into the frequency r square, and then the forcing applied to each of these would be sr. So the coordinate corresponding to this would be the xi r. So this is very interesting in that now I have a number of single degree of freedom system, and the normal modes have transformed a multi-degree of freedom system into a set of single degree of freedom systems. So that's what has happened here. So this is so important that I have taken a slide to write it down, because you must remember this fact permanently. We have transformed a multi-degree of freedom system into several single degree of freedom systems. This decoupling of the equation is due to the diagonalization of the matrices, which has been achieved by normal mode transformation. So that is the mathematics which is happening here, that the phi t m phi, the phi t k phi are essentially coming out as diagonal matrices. Now here we have taken 2 mode solution, but if you were to take 4 mode solution, then you would get 4 1DOF systems, and that would be an exact duplication of the multi-degree of freedom system, which is a coupled system. So essentially if you were to take a 4 mode solution, you would get a 4 single degree of freedom system, which would be exactly same as the multi-degree of freedom system. But the primary advantage comes about in this modal truncation. We typically do not want to retain all the modes. So now one thing we have to consider are the initial conditions for the problem. So Recall the first system in which we were dealing with W. So there at T is 0, W was W0, W dot is W dot 0. And so using our expansion here, what I do is pre-multiply this by phi Tm phi Tm, and so I get this equation here. So essentially I take phi transpose M, multiply it here, so I get W, I get here this term, and this term again diagonalizes this mass matrix, and so I get here something like this. So from this I can obtain two equations. I can obtain this xi1, the first modal coordinate, in terms of m1, and this equation here, and xi2 in terms of this equation. The whole point of this exercise is to express the modal coordinates in terms of the actual coordinates w, which are there for the differential equation for the system. So again, we can say, as far as initial conditions are concerned, we can take these two equations, substitute 0 here, and then we can write this equation out in terms of w and w dot 0. So now if you were to use these initial conditions with the modal equations, you would get the response of the system, and the response wt has modal components, which would be the xi1 and the xi2 here. So what does this mean in practice? This means in practice that if you were to take all modes, or you were to solve the basic differential equation system, you would obtain a certain response, which we will call the actual response. If you are going to take only one mode solution, you may get something here. If you get two mode solution, it may become closer to the actual response. Three mode solution would become very close to the actual response, and four mode solution would exactly coincide with the actual response. You could also get the modal component of each response here. So the modal component would be the xi1, xi2, xi3, xi4 if those are present. So essentially this lets you think about the dynamic system in a different space. So essentially all you have done is, instead of viewing them in the coordinate system corresponding to W, which are the actual degrees of freedom in the system, you are viewing them from the modal space, which are these xi coordinates. So these can be thought of as a different coordinate system where these equations are essentially decoupled. So now what's the practical advantage of all this mathematical jugglery that we have done? Well, one of the things which we have done is that we are able to reduce a multi-degree of freedom system to a few 1DOF systems. But if we were simply to use the same number of systems, then the advantage would only be in terms of getting neat solutions and not necessarily in terms of anything else. So the fundamental advantage in terms of practicality is that we typically need only a first few modes to properly capture the dynamics of a system, or properly describe the response of a dynamic system. So if we have a system which has 10 degree of freedom, maybe 2 to 3 modes are sufficient. And you need to do some kind of convergence study here to see that you need to first do a 2 mode solution, then a 3 mode solution, then a 4 mode solution. And you will soon find that after a few number of modes, if you add an extra mode, it doesn't change the result much, or there is a negligible change in result from going from a certain number of mode to one more mode. And at that point you can essentially say that your modal convergence has taken place, and then you use that number of mode for your problem. So this is a key simplification which reduces the problem size of most structural dynamics problems. So just to end with a practical example, let us say we have a wing, or it could be a rotor blade or some structure. Now, typically you would create a system with a large number of degrees of freedom, whether you use a Landmark system or a discretization method, you would have a large system. Now, if you were to form the mass and stiffness matrices of this particular wing, it may be a very large size matrix. It may have 100 degree of freedom, it may have 1000 degree of freedom, or even more. Now what actually happens physically is that the first few modes, maybe just 5 or 10, may be enough to describe the response of the system. And this happens because typically the forcing is such that only the first few modes get excited by the forcing. And in those cases, we can typically only keep a truncated set of the first few modes, and we can use our physical reasoning to get these modes. So we may take some bending modes, we may take a few torsion modes, and then we are well set with our problem. So this is a huge simplification in structural dynamics, which is widely used in solution of many response problems and also problems in flutter and divergence and so on. And it really helps the life of people who are dealing with dynamics. Of course, remember that we are assuming to a large extent or to complete extent that these are linear systems, so things are all working out very well. So for linear systems, we can certainly say this is a good way to go about it. Modal truncation is the way to reduce the size of your problem. So I will end this lecture here. I will see you in my next video.